Hello and welcome to the Summer of Innovation web series. I am your host, Kurt Hogan, coming to you live from the NASA Langley Research Center right here in Hampton, Virginia. You know, you can catch us here every Tuesday and Thursday. That's Tuesday at 11 o'clock a.m. Eastern Time and Thursday at 4 o'clock p.m. Eastern Time. And we will bring you an exciting researcher, scientist, or what else do they do? They're researchers, they're scientists, and there are engineers that will bring you something very exciting to hopefully inspire you to learn all you can about math, science, technology, and engineering. And we will bring you somebody very special each and every one of the webcasts from one of the NASA centers around the country. And today is no exception. We've got something really exciting for you, and we want you to participate. So in order to participate, all you have to do is go right to your computer and email us at nasalearn@gmail.com. That's one word, nasalearn, N-A-S-A-L-E-A-R-N, @gmail.com. And our presenters will be happy to answer your questions right now or right during the webcast. Let's not waste any time. Through the power of NASA and the Digital Learning Network, we are going to take you back in time to introduce you to the Wright Brothers, or somehow bring them from the past right here into the present. So let's shoot it right over there to Wilbur Wright. Wilbur, can you hear? Or wait a minute, is that Orville? Orville, is that you?
It's me, Mr. Hogan. That's amazing that you can all reach back here to 1910 and have me talk to you in the future. Is it possible that we could include my brother Wilbur in Dayton?
I think so.
Okay. Well, we would like to talk to your students today. Oh, there. Hello, Wilbur.
Hey, Bubs, how we doing?
We're doing well here. Haven't sold the airplane yet to the Army, but still working on it.
Good. I knew the Virginia work was going to go pretty good.
Mr. Hogan here has contacted us and would like us to talk to the students here who've tuned into, I guess he calls this a webcast, about our process of inventing flight. Do you think we could do that?
I think it'd be a lot of fun, yes.
Well, you wrote me about some pictures, you said.
Yeah, when I got back from Paris, I was digging around in the garage, and I found a lot of pictures that most of them you had taken over the last 8 or 10 years. And it sort of tells the story of what we did in the invention of the modern airplane. Let's see if we can bring those pictures up. Let's see.
It was a difficult story. We're going to look at a story here about the factors that we had to deal with in inventing an aircraft. Factors of lift versus weight, thrust versus drag. That last one, stability versus maneuverability, I think is kind of our early focus, don't you think?
Yeah, lift, weight, thrust, and drag were fairly well understood, or at least we thought they were well understood when we began. There had been previous researchers that had looked at building a machine either with enough power to get it off the ground or perfecting the lift and drag through glider experiments. I'm thinking, of course, of Mr. Hiram Maxim and Herr Otto Lilienthal.
That's true. Mr. Maxim invented an aircraft that was really powerful. It weighed over 8,000 pounds. Can you imagine, with a crew of 4, powered by steam engines?
I thought those propellers were something to look at. 18 foot across, but they looked like great big windmills in essence. They didn't know much about propellers in those days, did they?
No, not at all. And it turns out that this actually lifted off the ground, went about 900 to 1,000 feet, but crumpled over on its side, and having spent $250,000, Mr. Maxim just walked away. Now, the other thing besides power was this story. You want to tell people about Herr Lilienthal?
Sure, the understanding of lift and drag. And when we look at this picture of Herr Lilienthal and some of his glides, he was an engineer in Berlin and published data, took a lot of data on the shapes of wings and how much lift a wing would create and how much drag the wing would create. And he put his data and he put his tests to the tests by building flying machines. And he used to climb up that hill that we see at the lower left and take long glides. Now, both Herr Lilienthal and Mr. Maxim built their machines rigid, which meant that to steer the aircraft, they would have to adjust the weight, adjust where the pilot hung. And during one of these flights, Herr Lilienthal was killed in 1897. And it interested us because it indicated a problem that needed to be solved. It looked like people were understanding lift and drag, a little bit about thrust, but not so much about how to keep that aircraft balanced in the air. And we had some ideas on that. Being bicyclists, we understood that when you ride a bicycle, the pilot's involved. He's not just along for the ride. So we thought if we could sort of change the shape of our wings, maybe we could make a contribution. In the beginning, that was all we were going to try to do.
Exactly right. I remember you had, well, we were kite flyers, bicyclists, kite flyers, and we built a kite in 1899 that you flew, and your idea was that we might achieve lateral control. That means kind of going left and right in an aircraft by twisting the wings. So we tested it out. This was, what, about 5 feet across, wasn't it?
Yeah, it was a lot of fun. I used to chase children that would come to see us fly. They thought they would see a regular kite that was at the mercy of the wind, but by using our controls, we could make that kite move through the air in the direction that we wanted it to go. And the thought was, well, if we could make this a little bit bigger, from 5 feet maybe to 25 feet across, we could fly. We could get on here and fly. Now, Herr Lilienthal, to his credit, worked for 5 years and had about 5 total hours of flight time. We thought that maybe if we went to a place windy enough and flew the aircraft as a kite, that we could get maybe 5 hours in a day or 2 days at best. I think you contacted the Weather Bureau, didn't you?
We wrote to the Weather Service, and at the time they said the winds, we were looking for high sustained winds, fairly unpopulated area. They set back that the Indiana Dunes on the shore of Lake Michigan and the dunes at Kitty Hawk in North Carolina were the places with the highest sustained winds. Now, we'd never been to Kitty Hawk, but we thought that would be a nice vacation. So I remember we built an aircraft in Dayton, about 16 feet across, and carted it down to the Outer Banks. And here's a picture of our camp. Set up, that's you washing the dishes with sand. There was a lot of sand there, and lived in a tent for a number of weeks. And we had our aircraft. This is the aircraft, like I say, about 16 feet across, and we were able to fly it a lot as a kite, which we were doing here. We were thought originally to hang this from a tower and get a lot of practice just gliding, hanging from a tower. But this is what we ended up doing, flying it as a kite. On the last day we were down there, I remember you got 12 flights on this, but it was just not providing the lift. In fact, we even put one of the local fishermen here, little Tommy Tate, whose father kind of helped us out that first summer as a pilot, sitting on that kite and actually lifted him up, but most of the time with chain, and realized that we just weren't getting the lift from the data that we'd gotten from Herr Lilienthal. So the next summer, back we went.
Yeah, we understood from information that we got from Professor Langley at the Smithsonian, we had a little understanding of the mathematics behind flying, and we knew that the amount of lift that a machine would create depended on the area of the wing. We had a rectangular wing, and there were 2 ways to make that rectangle bigger. We could either make it bigger from tip to tip or bigger from front to back. And even though we're the Wright Brothers, the first time I think we got it wrong, because we made the aircraft bigger front to back, built a whole new aircraft, put it on the train, went back to Kitty Hawk. We were a little anxious to get there this second year, and went in the middle of June, which was sort of bad from a mosquito standpoint. Also ended up being kind of bad from a flying standpoint. We still didn't seem to know what was going on.
That's exactly right. When you look at this 1901 glider that we put together, and there I am with holding it up on the left. This is how we flew. We went to the top of the sand dune, and with a pilot on it. You were the pilot the first 2 years, and we kind of flung that thing off. And as you glide down the hill, we did a lot of measurements of the angle of the glide, the length of the glide, the time in the air. And we did get a number of glides on this, but our calculations showed, again, this only provided about 1/3 the lift that it should have provided. And it was pretty discouraging, having spent a couple summers at Kitty Hawk, that we had not succeeded in doing very much. In fact, this aircraft even performed kind of poorly on occasion by spinning into the sand unexpectedly, I remember.
Yeah, and as I remember, I was asked to go do a talk to some professional engineers about what we were learning, and I was going to find it relatively embarrassing, because I think I told you on the way back on the train back to Dayton that I thought people would never learn to fly in our lifetime. There were too many problems. We would only be able to get one new aircraft every year. It just looked like it was going to be too expensive and too difficult, and I was going to have to get up in front of professionals and tell them this problem looks too difficult.
Well, we knew
But
something
then we
was
began to
wrong.
question the data.
That's
we started
right.
to look at our own data, and you had a good idea on this one.
Well, we thought that the angle that the wing had to be set at to balance a flat plate, there was something maybe wrong with that, so we decided to test it in Dayton. We tested it on a bicycle. Now, we were bicycle salesmen and mechanics, so on the front of the bike, we mounted a wheel horizontally, put a flat plate on one side, and set the wing model and at the other side, and it did not balance at just the right angle. It was supposed to balance at 9 degrees, and it had to turn it to 16 degrees to get it to balance out the flat plate. So having that in mind, and knowing that things were needed to be changed, you went ahead and did the talk, and while you were gone, I started working on one of these, and that's a wind tunnel. Now, wind tunnels are interesting because in a wind tunnel, when you don't have to have a full-size plane to do tests. We made, as you see at the bottom, scale models of wings out of pieces of metal and mounted them on a balance inside the tunnel and blew air over this and measured the performance of different combinations of wings, different sizes, different shapes of wings. We did what are called today in engineering parametric studies. We made comparisons of, in the bottom here, all these wings had the same area, but some were long and thin, some were short and fat. And we found out after about 6 weeks of testing we had made a mistake in 1901, as you said, going to wide wings. We needed to go long and thin on wings. It has to do with the amount of drag an aircraft creates when it goes through the air. And long, thin wings create less drag. So, in 1902, we built another glider. Tell them about this one, Will.
Well, this is the basis of our fortune, or as you well know. This was a unique machine. It was the biggest glider that anyone had ever built. It was about 30 feet from tip to tip. And we had the what was called the pitch control. We could make the nose go up and down by that little wing in the front. And then we put a tail on the back, which you correctly understood had to move as well to allow us to make nice coordinated turns. We could twist the wings, twist the shape of the wings using our hip cradle, and on that picture at the lower right you can sort of see that the wing is twisted. I'm banking, I'm making a nice turn, the rudder's keeping me go smoothly around the turn, and at the end of that year we had set all the records. We had the biggest machine, we'd flown the longest, we had flown the farthest. In fact, each of us, I'm thinking maybe about 1,200 flights that year. It seemed like each of us got more than 500 flights. We were the most experienced pilots in the world at the end of 1902.
Well, it's interesting. That machine in 1902 was the first machine anyone had ever made that could be controlled in 3 axes. So if we look at our model here, we can see that we can control the pitch going up and down in the nose. We could control what is called roll by twisting the wings, going side by side, and we can control yaw, pointing the nose left and right. And no one had ever done that before. And having figured that out, we decided that all we had to do now was add an engine and propellers, and we were ready to fly a powered aircraft. Now,
yeah, we had the wind tunnel data that would tell us exactly how to scale that up. We knew our math. We knew the basic science behind it, and we had the best data in the world from that 6 weeks of testing in 1901. Yeah. But we needed an engine, and you'd have thought that that would have been easy to do. Automobiles were being invented at that time, but nobody wanted to build us or sell us an engine.
Well, fortunately, Charlie Taylor working for us in the bike shop, and Charles Taylor was our mechanic, and we worked with him to build a 4-cylinder engine with an aluminum block. Most engines at the time were made out of cast iron blocks and very heavy. This was about a 200-pound engine, very light for its time.
Yeah, I believe it, when we put it on our test device, we found that it made about 8 horsepower, was about 200 pounds, and all we had to do then was do just like we had done in 1902, lay on the wing, decided to put the engine next to us. We did made too many crashes, 1901 and 1902. I didn't want to fall on the engine, and I didn't want the engine falling on me either. So we put the engine right next to us and hooked up a couple of propellers. The propeller theory was very interesting when we had to work that out. That was a lot of arguing between us. But with two sets of eyes looking at a problem, you can always kind of figure it out better. Teamwork between the two of us, I think, was the key on that point.
Exactly right. We used the wind tunnel data to figure out that the big flat windmill-looking things that were used before by Mr. Maxon were not the way to go. That we needed propellers that needed to be basically a rotating wing. That we needed a wing shape to turn through the air. And so we'd made long, thin propellers. We knew things needed to be long and thin because of our drag calculations. And these propellers are about 80, well, not sorry, they're about 60% efficient, 67% if I remember. And they were chain driven. They had to go in opposite directions, so we had to cross one of the chains. And this aircraft was ready to fly, except we kept bending the propeller shafts and sending back to Dayton for new shafts till finally it was until December of 1903 that we had winds we thought high enough, and we wanted to get home for Christmas, we'd try and fly this. And if I remember right, we tossed a coin to see who would get the first flight. You seemed that was the only fair thing to do.
I thought I was the winner that day, but the winds were very light on the 14th of December, so we put the airplane up the hill that you saw in that previous picture, laid out our launch rail, which was just a simple 2x4, put the plane up there, fired the engine up, and I made sort of the classic piloting mistake. As I took off, I tried to get up too high, too fast, pulled back on the controls, stalled the aircraft, which means that the air quit flowing over the wings, fell right back to earth and broke the nose. And we decided that wouldn't count as a flight. We repaired the aircraft, and on the 17th of December, we're ready to try again.
The 17th was an interesting day because the winds were 25 miles an hour that day, and pretty stiff winds. But we got help from the lifeguard station. They came over. We set up a camera, and Charlie, Big John Daniels, and he was worked there. He had never taken a picture before, but I told him just to squeeze the bulb when the plane got to the end of the rail, and he took this picture, maybe the most famous aircraft picture taken of me just lifting off. In fact, the winds were so strong, the aircraft had a speed itself of just 7 miles an hour from the engines. And
yeah, I was able to run right beside the airplane with you.
That was, so that flight went about 100 feet in 10 seconds. We did 2 more shorter flights, and then finally you had a flight of nearly a minute, 59 seconds and over 800 feet. Unfortunately, the aircraft got picked up in the wind and crumbled over and broke the engine. We had to come back to Dayton. But in another 2 years of work in Dayton with powered aircraft, we finally succeeded in changing the design, making bigger engines, till we got an aircraft, if we take a look here, that flew for half an hour. We could fly this aircraft until we ran out of fuel.
Yeah, those are nice pictures. I believe you took most of those pictures out there at Huffman Prairie in Dayton, Ohio, right at the end of the trolley line. We could fly pretty much alone. We didn't have anybody spying on us. That 1905 aircraft was the world's first practical airplane. We could stay up until we ran out of gas. But we were worried that people would steal our design, so starting in 1905, we didn't fly for another 2 years. People over in Europe began to learn how to fly. Some of the information that they had heard of what we did, some of the people over in Europe began to copy those ideas, but they were always 2 or 3 years behind us. Yeah, there's a picture at the top from Alberto Santos Dumont. That looks like his number 14 bis.
The Voisin
Is
brothers.
that the Voisin brothers?
And the French flyers were unable still to control an aircraft in 1907 when You'd went over there and showed them our aircraft and showed them how we could coordinate turns, and they were just so amazed. We went into the aircraft business, out of the bicycle business, and became quite successful. It's interesting to note, if we come back to Wilbur and Orville here, that this series of testing, taking measurements, doing math, changing designs, making things better continues today. Because today, I'm not Orville Wright. Today, my name is Roger Storm, and I am the Education Coordinator at the NASA Glenn Digital Learning Network. My brother Wilbur.
In 2010, I'm Tom Benson, and I'm a senior research engineer here at the NASA Glenn Research Center. I'm actually speaking to you from Cleveland, Ohio, again sort of through the miracle of the Digital Learning Network. My buddy Roger there is at NASA Langley. I'm at NASA Glenn, and it's interesting because exactly the same techniques that were worked out by the Wright brothers 100 years ago are the same things that modern aeronautical engineers do.
The NASA Glenn Research Center in Cleveland, Ohio, where we both work, carries out aeronautic testing. And we have a picture of some of the things we do here. We'd like to share with you how we can look at the same things that are going on today as were going on over 100 years ago in the sands of Kitty Hawk and the bicycle shops of Dayton. This is an A3, isn't it, Tom?
Yeah, it's an S3.
S3, yes.
It's actually a reclaimed Navy aircraft carrier based. Usually, it had been used for submarine hunting by the Navy, but we use it actually for icing research. In the background there, you see Cleveland, and beyond Cleveland is Lake Erie. We're the only NASA center that's up in the north part of the country, and during the winter, that lake ices over. And doing icing research and making sure that you can keep an airplane in the air under adverse weather conditions is one of the big safety of flight concerns that we have within NASA. It's one of the things that we research here at NASA Glenn. And we use that S3 out over the lake to test some of the ideas for inhibiting the effect of icing on aircraft.
Yeah, in fact, we go back a long way with studying aircraft. If you think about after World War I, the government formed NACA, N-A-C-A, the National Advisory Council on Aeronautics, and you can see a picture here of our hangar in 1958, because in 1958, NACA changed to NASA. With the launch of the Russian Sputnik, President Eisenhower organized NASA, so here as we were painting out the C and getting ready to paint in the S to become one of the NASA research centers. Now, some NASA centers are flight centers. Some are test flight centers. We are a research center, so we investigate primary materials.
Just like NASA Langley as well. Langley was sort of the mother center. It was the first NACA center. NASA Lewis at the time was the third NACA center, and each of the NACA centers and NASA centers has a specific objective that they work on.
Tom,
at NASA Lewis Glenn, it's power and propulsion.
Tell us a little bit about our center here. We'll take a look at NASA Glenn.
Yeah, there we are located right in Cleveland across from Hopkins Airport. And you'll notice that there are a couple buildings that really stick out. That's where we're talking to you, where I'm talking to you today from. That's our Research Analysis Center, or our Computer Center. Computers are very important now. The Wright brothers used to be able to do their calculations with pencil and paper and a book of tables. Today we do most things with computers, and that houses our big computers. In the background right behind that you see a wind tunnel. And wind tunnels have grown from the days of the Wright brothers. The Wright brothers tunnel was about 6 foot long. This one is as long as a city block. And actually the models we put in this tunnel are larger than the entire Wright brothers wind tunnel. That is the 8x6 wind tunnel. So its test section is 8 foot tall, 6 foot across, and the air going through there can go about 1.5 to 2 times the speed of sound. Over on the right side is an even bigger tunnel. The Abe Silverstein tunnel, what's known around here as the 10x10 tunnel. Its cross-sectional area of the test section is 10 foot tall, 10 foot across, and about 50 foot long, and we can blow air through there at 3.5 times the speed of sound. It's so big we can put whole inlet, engines, and nozzles all together in the one wind tunnel and actually test an engine while it's burning. So we can do all kinds of perfecting of the components that go into a jet engine.
So if I calculate right, that's air going about 2,500 miles an hour?
That's right.
Wow.
Fastest air-breathing machines were tested in our NASA 10x10 wind tunnel.
Well,
we may have some pictures of models in the tunnel, I think, as part of the talk.
This is, well, the Wright brothers did propeller research, and here is a model in the tunnel of a propeller. Tell us about this.
This is a new kind of propeller. This is called an unducted fan, or a UDF. And it was an idea that we first started looking at during the fuel crisis in the 1970s, but it's coming back as fuel prices continue to rise. Propellers, as it turns out, are actually much more efficient. They can get more thrust per pound of fuel than a pure jet engine. It's because they move a whole lot of air. And this propeller, most propellers from the times of the Wright Brothers up through World War II, the speed of the propeller and the speed of the aircraft are limited. If you started getting shock waves that form at high speed on the propeller, you'd lose efficiency. But during the 1970s, we looked at these unducted propellers, and using new materials that could make the blades very stiff, we can actually run one of these propulsion systems at about 8/10 the speed of sound for the vehicle, and over the propeller itself there are shock waves. On the spinning part of the propeller, the flow goes faster than the speed of sound. You get shock waves that form. Now normally that would cause you some problems, but with this research we can actually push the propeller on out into the higher speed. So we looked at in the 1970s, and we're looking at again the possibility of incorporating these things on a regular airliner. I think we have a picture there of one of these propulsion systems put on a 737. So you would see, again, a turbine engine to turn the propeller, but you would have a very high-speed unducted propeller back there. Now, one of the things we worry about with that is the propellers, any kind of propellers, make more noise than a jet engine. And noise is another one of the big areas of research that we're involved with here at NASA Glenn, to try to keep things quiet.
Well, before we get to the noise, and let's not leave propellers yet, but you spoke back in the 70s. We did some other research back in the 70s that's becoming popular today, and we started building the first, well, modern windmills, I guess you'd call them, wouldn't you?
That's exactly right. Windmills being used to generate power. You can either have the motor turn, run an electric motor and then turn the propeller, or in this case we let the wind blow the propeller and let it turn the electric motor, and it will generate electricity. So more and more you're beginning to see farms of windmills, modern windmills, not the kind you see from Holland that were used many, many years ago to grind corn and stuff like that, or grind wheat. This is actually used to generate electricity, and we're beginning to see farms of that. A lot of the basic research was done here at NASA Lewis at the time, and unfortunately the Europeans seem to have picked that thing up, and a lot of the windmills that you see here in the United States are coming back to us, being sold back to us from the Europeans. But the research in how to make those and how to do that better was actually done here from NASA.
Excellent. We mentioned engines and being noisy. We have a jet engine here to look at that shows a number of different fans and blades, and looks pretty complicated, but air blows through this and the things spin at a very high rate of speed. A lot of RPMs here, which generate a lot of noise, which anyone that lives near an airport is very familiar with. So some of the research done here at Glenn is related to this interesting structure. Tell us about this.
Yeah, this is our aeroacoustic propulsion lab. So again, it's a big geodesic dome, and on the inside of the dome, it's an anechoic chamber. And anechoic's just a word that means we put in materials that will absorb noise. So it's kind of fun. You can go inside here and yell your head off, and it's like you're yelling into a pillow. In fact, the inside of that looks like it's covered by thousands of pillows to absorb sound. And what we do is we put a whole engine in here, or one of the components, and oh yeah, you can see all the pillows there, and we can tell exactly where the noise is coming from. Normally, if you have a whole jet engine and sound can bounce around, and it'll bounce off the ground, it'll bounce off other parts, and it's hard to pinpoint what part of the engine or what part of the propulsion system is causing the noise. With this facility, we can identify that and go in and do things to cut down the noise. One of the ideas we came up with was called the chevron nozzle. So on the back of a turbofan, you'll see that rather than having a nice straight edge, we sort of serrate that edge. And you'll notice it isn't even uniform. It's different shapes of serration, or different shapes of wiggling back and forth around the nozzle. And what that does is when it flies through the air, as the air goes by there, it mixes the air from the outside and puts a little sheath of mixed up air going around the engine, and it creates, again, kind of a buffer zone. It keeps it nice and quiet. That's actually the new Boeing 787 Dreamliner. It's going to be one of the first aircraft to fly with our Chevron nozzles for noise suppression. So you'll notice, even though it's got a very big engine, this aircraft is going to be 20 to 30% quieter than even smaller aircraft.
There's back in the wind tunnel then.
Yeah, we know that the back end causes noise, but there's also noise that comes out of the front of the engine. So this is looking at various kinds of noise suppression materials that we put in the inlet, or the front part of the engine, to keep noise from propagating from that fan upstream, so that whether the airplane is taking off away from you or towards you, you'll have the quietest environment we can provide right now for people on the ground. Again, it's being done in the wind tunnel, the same as the Wright Brothers.
Well, here's another wind tunnel view. Is this lady in the wind tunnel here?
Actually, she's outside the wind tunnel. Even as with the brothers, you don't get inside with the model. The air going down through those metal walls that you see there could go 2.5, 3 times the speed of sound. So you wouldn't want to be inside with it. That's an inlet, or the front part of a propulsion system that we were studying for a supersonic transport. So far in the history of the world, there's been one viable supersonic transport, the Concorde. I believe there was a Russian one as well, a Tu-144. But we were looking at maybe advancing that technology and allowing people to fly higher, farther, and faster. And a lot of it comes down to what goes on right in front of the engine. That's, again, a wind tunnel model to test that.
Well, here's an interesting tunnel here. NASA Glenn has the world's premier icing tunnel. And here's the guy that's in the tunnel now. You said he stayed outside, so tell us what's going on here.
Well, this is after the wind tunnel test. This wind tunnel is kind of special. Inside the wind tunnel, the big circuit, there's a refrigerator unit that makes the air inside the tunnel down around 25 degrees Fahrenheit. And those are the kind of conditions that exist at altitude, low altitudes, for airplanes. And what we do, we have a spray bar. We create supercooled water droplets, and we spray a nice uniform spray as if you were flying through a cloud. And then the air, cooled and wet, flies over the model, and ice forms on the model. Now we test, and we can watch you'll see the guy to the right is actually outside the tunnel, and they watch for the ice buildup. And as soon as the ice gets built up like this, they'll stop the tunnel real quick, put on a parka because it is cold inside that tunnel, even in July. And then he'll run in and he'll do different measurements of how the ice formed, what the shape of the ice is. And we look at various techniques to keep ice from building up. If you had an ice buildup like that on an aircraft, that aircraft would be in danger of crashing. So our idea here is safety of flight. Find out how ice forms and look at the devices and things you can do to keep ice from forming on an aircraft. We do it with models. It's much safer and cheaper to do it with models.
Well, this is a familiar model. I recognize this. This is the back of the space shuttle. And
go ahead and tell them about the model. It's kind of cool.
We were concerned at the time with how the gases came out from the engines and would it affect the flight of the space shuttle. So we actually had little engines built. Now this model cost probably over $1 million to build. This is not a model like you'd make from the hobby shop, and it's exact scale flying model. And the engines could burn inside the wind tunnel, and we could tell how the gases would flow out the back and how this would fly. Engineers put a lot of taps. You can see these lines coming out on a model so they can tell what the pressures are across the wing, across the nose, and this is how we collect data coming off a model in a wind tunnel. The Concorde made a big sonic boom when it landed, and So it had to land in airports far away from where people lived. And so this is an attempt to put a real long, thin nose on an aircraft and see if that would help mitigate or do away with or lessen the effect of a sonic boom. So lots of engineering going on, lots of research, and lots of changing of models of aircraft. Now, we don't do everything in the tunnel, do we?
No, actually, it's interesting. The big tunnels that we're talking about, as big as a city block, some of those things may cost $500,000 a week just for electric charges to run the tunnels. The models cost several $1,000,000. And we're always trying to do the best we can with the least amount of money. And one of the things we found out, in fact, it's the area that I actually work in my job here at NASA, is an area called computational fluid dynamics, which means using computers to study how air moves. There are mathematical equations that students study. When I first started in engineering a long time ago, 40 years ago, the best we could do was kind of neglect some terms and simplify things down and do very, very simple problems. But as computers have become more and more powerful and more cheap, we're able to go in and solve those equations using big computers, and you'll see a picture like you saw there that can give you a lot of detail about what air is doing in a rather complex situation. Now, this helps us actually to build a better model. The state of the art is we still want to see something fly before we put people on it, and we still want to test it in a wind tunnel before we make something that we're going to go try to fly. So the computer analysis normally predates all of that. We'll do a lot of our what-ifs, a lot of our trade studies. When we were talking as the Wright Brothers and showed those 3 or 4 different models to study a problem, rather than build 3 or 4 or 5 or 10 space shuttle models, we'll do it with the computer. And we'll pick the best design from that and then put that in the wind tunnel. And we'll do a little tweaking on that and then finally build a great big aircraft to go fly.
So going flying is still the bottom line.
That's what people want to do. We still want to go fly. It was true in the day of the Wright Brothers. It's true today.
Well, thanks for all your explanations, Tom. We appreciate your time today. We'd like to let our students know what it takes to become an engineer. Could you tell us a little about your background and how you got to where you are today?
Sure. I'm an aerospace engineer, and to become an aerospace engineer, it's kind of funny. It actually starts when you're in 3rd, 4th, 5th grade. You have an interest in things that fly. You fly kites, you build model airplanes, you build model rockets, you read everything you can find. That's what happened with me. I used to like to go to science fiction movies. I built lots of models, and I was pretty good at science and math. I liked math. Math was fun. I could see what was going on with math. My teachers made me do my homework a lot. I fought them a lot. But years later, I found out my teachers were right. If you put in the time and you work hard in grade school and work hard in high school, it'll allow you to go to college. And to become an aerospace engineer, you've got to go to college. So when I went to college, I was pretty good at it. And I actually got to work for the department. I learned a lot of things in college. I went in the Air Force for 4 years and worked on fighter planes, worked on bombers and stuff like that. It was kind of fun. And then I got my dream job, which was to come here to NASA. And I've been at NASA here in Cleveland for 30 years. And it's a lot of fun. I still have fun doing this. I think Orville Wright once noted that it was amazing that there were so many things that were still to be found out, still to be learned at the time of the Wright Brothers. Well, that's still true today. There's a lot of things we want to do, and we don't know how to do them all. And it's going to take a lot of smart engineers and scientists and teachers to do that as well. You want to tell them how you got here, Roger? It's kind of interesting.
Well, I came in on the other end of things. I started out as interested in science so much that I wanted to teach science and taught high school science for a number of years. and close to NASA Glenn. So I got the opportunity to work at Glenn in the summer times, to work with engineers like you and develop software and programs to help students learn. And today I work in distance learning, which is what we're doing right now, where we connect with schools and bring people like Tom Benson into your classrooms to tell you the story of the Wright brothers, to tell you the story of NASA Glenn, the story of Galileo, so many things about our solar system and other things that NASA is learning about every day. Mr. Hogan, thanks so much for having us with you today. We appreciate the opportunity, so we'll turn things back over to you.
Well, thank you so much. It's been a really good time listening to all the stuff about the Wright brothers. We've got a couple questions. I don't know if we have time for them. Do you have time for the questions?
Sure, let's take a couple questions.
All right, I've got 5 of them, actually. I'll give them all to you at one time, then you can just pick and choose from there. Is that easier?
That's fair.
All right, I'll tell you who sent them to, because I know you guys are at home, want to hear your names. So we've got Christopher from Orange, New Jersey. We've got Justin or Justine, I think it's Justine from Charleston, South Carolina. We've got Lance from Detroit. We've got Kevin from Fort Lauderdale, Florida, and Ellen from right here in Hampton, Virginia. The questions are as follows. The first one, did the Wright brothers think we would be as advanced today as we are 100 years later? Do you think? I guess you'd have to just suppose. Mm-hmm. The other one is, if it weren't for the Wright brothers, do you think someone would have eventually figured out how to fly? Lance's question is, did they have paper back then? And if so, could they have made paper airplanes and copy those? Kevin's question is, did the Wright brothers make a lot of money from their invention? And Ellen wants to know, how high did the Wright brothers' plane actually go? Did you get all those?
Got most of those. If we don't cover them, Mr. Hogan, you fill us in again. Okay?
All right, we'll do.
We can answer all 5 of those questions pretty well, I hope. So
okay.
Let's start with the paper idea. I was intriguing. The Wright brothers were actually inspired by their father, who in the year 1877 came home with a little model helicopter. It actually worked by winding up a rubber band, letting it go, and had a propeller at the top and fly up to the ceiling. So models at the time were important. They did not make paper model airplanes, okay? The models they made needed to be durable. They needed to be able to work in a wind tunnel. And, you know, paper airplanes you can fly a few times, but they wanted something they could really test and take measurements on. So that's why they made the metal wings that they tested, okay? But paper airplanes sure are fun, and you can do some things with bending the wings and the tips and things and find out some things about how airplanes behave in the air. That's a lot of fun to do, okay?
Do you want to tell them about how much money you made since I was dead?
Okay, well, unfortunately, Wilbur died in 1912, and Orville lived to 1948. And when he sold the aircraft company they formed in the year 1915, he sold it purportedly for about $1.5 million, which would be hundreds of millions of dollars today in today's money. And so Orville became very wealthy over the invention of the airplane. Your question about whether the airplane would have been invented at all had it not been for the Wright brothers is a very interesting one. Of course, as Mr. Hogan said, we have to speculate about that. But one of the things about being brothers, okay, about me and about having a brother like Wilbur, is that we bounced ideas off of each other. And people were starting to unlock the secrets of airplanes, but doing it very clumsily. The Wright brothers came along and in a very short period of time solved a number of problems that people had not seen up to that point. I would imagine, Tom, that probably with time these secrets would have come about.
I think they would have probably figured it out within 10 years, because the Europeans sort of independently come up with flying machines. Now, the Wright brothers kind of sped that development up, particularly with the propeller development, and particularly having the wind tunnel data. But the Wright brothers wind tunnel was not the first wind tunnel. There were actually 10 wind tunnels. Theirs was the 10th wind tunnel in the world. 3 of them were in the United States, and 7 of them were in Europe. So it's my feeling with the run-up to World War I and the like, that probably they would have had flying machines within 10 years of when the Wright brothers. That'd be my speculation. You ask about how high the Wright brothers flew. And like everything else, you start out small and you get higher and higher. The ones at Kitty Hawk were only about 5-6 feet off the ground. When they were flying at Huffman Prairie, they had to fly over trees. So they got up to 25, 35, 40 feet. By the time we were selling aircraft to the Army, there was a requirement that you carried an observer, and I believe there was a thing published when Orville Wright flew more than a mile high. So he went about 5,000 feet up in, I believe it was a 1908 or 1909 aircraft, which sort of looked the same as the 03, except that the bigger engine, the pilots could sit up, and the observer could sit up next to him, and they could stay up for a longer amount of time. It had a bigger engine. So at various years, they flew to various altitudes and various lengths of time in the air as well.
And the last question, I think, is would we be amazed, would the Wright brothers be amazed at what has happened in a short period of time? And I think absolutely yes. In the space of less than 100 years, okay, and the space of actually less than about 50 years, we went from very slow bi-wing cloth covered frame aircraft to jet planes and flying faster than the speed of sound. And I think that would be a most amazing thing.
There's one thing, though, I think they would be disappointed, and that is that the Wright brothers thought that flying was so fantastic that everyone would want to fly. And I think like when Roger and I were young, there used to be things in popular science that predicted by the year 2000 we'd have flying automobiles and everybody would be flying instead of rolling along the ground. And I'm kind of disappointed that it's 10 years after 2000 and we're no closer to me being able to just go out and fly across the lab than we were 50 years ago. So, there's some disappointment, some interesting.
When I was in school and when you were in school, if you asked a class how many of you have been in an airplane and flown, you might see 1 or 2 hands go up. In the space of the last 40 years, when we go into classrooms and do teaching, we ask, you only see 1 or 2 hands stay down. So in this country, a large number of people have had an opportunity to fly, and so that's gotten very interesting. We are seeing a lot of advances, and as Tom said, one of the things that we probably like to leave you with is the fact that not everything's been discovered, not everything is as good as it can be. Not everything is as efficient, as quiet, as powerful as it could possibly be, and that's why we need you guys in school to be concentrating on science and math, to become the engineers of tomorrow. They're going to build these aircraft that maybe you'll all fly across the lab. So thanks for having us today, Mr. Hogan. If that's all the questions, why, we'll fade back into the past.
Yeah, I got to get back to work.
Thanks so much, Wright brothers. We certainly do appreciate that. It makes me wonder where we'll be 100 years from now. Thank you so much at home for joining us here for Summer of Innovation. You can catch us here every Tuesday and Thursday. That's Tuesday at 11 o'clock a.m. Eastern Time and Thursday at 4 o'clock p.m. Eastern Time. And again, my name is Kurt Hogan. I'm your host. We've been coming to you from NASA Langley Research Center, and we'll see you again next week. Till then, bye-bye.